Okay, so unit 3, designing experiments. So our first half of the unit was figuring out ways to gather information from a population that already exists. So the population is usually something rather large. It's difficult, tedious, and oftentimes impossible to count everything. So we create a smaller sample the proper way, and we get decent predictions on what the actual population stands for. That was the first part of unit 3, and that's still going to be important. Now we're switching into experiments a little bit, and this is where we don't really have the information in front of us. So we want to set up an experiment in the right way so that the information we get is as accurate as possible. With experiments, the goal is, right, this is our overall goal with experiments, is to determine cause and effect. That's the overall goal for this. Okay, so everything we've done before this point, there's no causation. There's correlation, right? Things are related, happen to be going in the same direction, etc. But there's never been a definite, this does cause this to happen. That changes today with how we design our experiments so that we can start saying that A and B actually cause each other to happen, and here's how. Okay, so keep that in mind as we're going through it. It is a little bit definition heavy for the first couple of slides, so I apologize if you have carpal tunnel after this. There are 12 definitions we got to go through. We used to do a vocab quiz in this unit, but obviously we don't do that anymore because everybody has their notes, so what's the point? So you used to have to memorize all these things. You're welcome. There, COVID helped you out with something, so you can't say it's all bad. All right, let's see if the little bunnies will hop like they're supposed to if I got started again. Oh, they're hopping. And the smiley faces are in. Okay, there you go. You guys want to see it one more time? That's cool. Ready, one more time? There you go. See, now you can smile on your Monday. After this class, half you guys are done anyways for the day. All right, here's our first 2 definitions. Observational study versus experiment. What's the difference? Why do I care? Observational study. This is where you only observe outcomes without imposing any treatment. This would be like me sitting at the front of the STEAM Center on the bench out there and documenting what time you guys come in for class. And then drawing up the information and saying, well, studies show that those who ride the bus are 5 minutes later to class on average than those who drive. It would mean nothing because it's just an observation. I did not impose treatment on you. I didn't make you take the bus. I didn't make you drive your car. I didn't make you leave your house at a certain time or high school at a certain time or whatever. So while it's nice to, discuss, it has nothing to do with reality as far as cause and effect. It's a study. Excuse me. Experiment, you actively impose some sort of treatment in order to observe the response. So we are now affecting all aspects of our observation by running an experiment. Big difference. We want to focus more on the second one. So as we go through this, I will make fun of those studies you see in magazines that say, like, if you drink coffee, studies show that 25% of people who do have less heart attack. Okay, good. That's congratulations. You observed something. Doesn't mean that the coffee is making that the reason. So that's what we're going to talk about. You can see why Mr. G walks through life very cynical, like, yep, that's nice. All right, observational study versus experiment. I can't remember who it was when I was growing up. I think one of my aunts was always one of those ladies that was like, oh, I read this article in the magazine and, all the oils in your Snickers bars are causing you to die of heart disease. And I'm like, okay. Then I went and learned stats and I was like, I was right. There's no actual experimental evidence of it, unless they put people together. Right. Well, that was always there. I'm just like, whatever. But that's why I believe in personal liberty as far as the decisions you make should be your choices and not suggested. But we can talk about that later. That's a whole different fun discussion on government versus. All right, so definitions, observational versus experiment. All right, let's continue on here. So here's our premise for today. I've developed a new rabbit food called Hippity Hop. Aren't you excited? I promise it makes the fur of the rabbit soft and shiny. It increases their energy and 100% of their daily vitamins and essential oils, whatever that means for rabbits. That's important, that last part. Can I, as a random individual with this shiny new bag of food, make these claims? Not if I want to be legitimate and not get sued. So no. Okay. Why not? Because I didn't run an experiment. I just put some food out and I saw one rabbit eat it and then all these things happened. So therefore my food was that way. That's not a well-designed experiment. That's an observation. Okay. So what we need to do is get away from that mindset and think, how can we fix it so that we can make those claims? So what must I do? An experiment. So that's why we're going to learn that's important today. Okay, so you can make a claim, but if there's no experimental evidence behind it, the claim is pretty much worthless. So the goal today is to talk about how do we know the experiment is good enough to where we can make those claims. All right, so who or what should I test this food on? Well, if I'm claiming it's good rabbit food, probably the rabbits. It wouldn't do me any good to feed it to Matthew. If his fur turns all shiny, then okay, well, that's exactly. Thank you for being a good sport, Matthew. I appreciate it. What should I test it on? Sorry, what should I be testing? The type of food. I was thinking the same thing, but I'm usually like the only person with the extra wool coat on. It was like, how come you don't wear a jacket in the winter? I'm like, it's always on, sorry. All right. So this is the kind of questions we want to be asking for today. This is going to be a recorded thing. Sorry, that's why I like recording this class. All right, so number 3 definition is experimental unit. What is the experimental unit? It is the single individual, be it a person, animal, plant, whatever, to which the different treatments are assigned. So I like to think of it as the victims. So that's my experimental unit. Like I said, the first part here is a little definition heavy, and I apologize. Number 4, what is the factor? That's basically what we're testing. So it's the question that we're looking for. Is the food good? Bless you. Later on, we'll talk about fertilizer on farmland. So it'll be the fertilizer, that kind of stuff. The factor, what are we looking at? And then the level is the specific value for the factor. So sometimes there's more than one different variety of treatment. And we'll talk about this later with the perfect example for this later is going to be with the cake batter. We're going to test different things on what makes the cake cook well. And so there's going to be different levels because there's more than one thing that we're testing or more than one variety. So sometimes it's one, sometimes it's multiple. So the level is the specific value for that factor, how many of them that we have. All right, so experimental unit, the victims, the factor, what we're testing, in the level, the different varieties of the factor. I still think this is one of my favorite units that we do all year. So I don't know how you guys have been enjoying it so far. Maybe it's tedious, but this one, and when we get to hypothesis testing in the spring are probably my 2 favorite, because they're the most practical when it comes to just daily general living. Because I know some of you guys replied to the get to know you survey at the beginning of the year, so I just want to know how to read stats better or what the media is telling me about stats. And I feel like this unit and the one we do in the spring are the 2 best at just giving you a good general understanding of how it works, and then you guys can take it from there. Because there's definitely a lot more that we don't cover. All right, anybody else need to write this still? I just randomly talk to make sure everybody's got enough time. Cool. All right, and then on the next page, we've got response variable. This one's a review of what we've already talked about before. So response variable is what you measure. All right, this is similar from our unit 2 when we had the explanatory and the response variable. The response variable was what the equation gave us as a prediction. Same thing here, it's what you're measuring. So if I'm testing my rabbit food, the response variable will be if the rabbit, what it does. Does he get shinier? Does he have his essential oils? Does he get happier? All that kind of stuff. And then the treatment itself is the specific experimental condition that the different units get applied to them. All right, try to remember where I got stuck here. There we go. All right, response variable, treatment. Again, sorry for the early heavy definitions, but all these words will be used as we go through this first part here. Okay, so for our rabbit food, things to think about. What were my experimental units? What is the victims of my experiment if I decide to test my rabbit food. So who are we going to test it on? The rabbits, right? Just reviewing, making sure you guys are still good here. And then what's my factor going to be? What's the question I'm trying to ask or solve? If the type of food is any good. So that's my factor, right? And then what is the response variable? Basically how well the rabbits grow, how they look afterwards, their energy level, whatever, right? Their outcome from the experiment. All right, so what I'm going to show you, and these are not in your notes next, so you can sit there and take a wrist break and stretch it out. So what I'm going to show you is some bad setups for experiments first. We're going to talk about why there's some issues, and then we're going to slowly transition to what are some things I need to do to make my experiments good. Okay, so when I say experiments in this class, again, I'm not talking about getting out the Bunsen burners and the beakers and we're mixing chemicals and we're going to watch stuff explode. As fun as that is, we obviously don't have a lab in here. So we're talking more practical application of administering treatments and that kind of stuff. To whatever experimental group we want. So sometimes, I don't know if we'll get to do our, or if that's just on level. We did an experimental project last year that was a lot of fun. I don't know if we'll be able to do it this year just because with the COVID stuff. Because last year people got to experiment on their classmates. It was kind of cool. And it wasn't anything dangerous. All right, so here's a bad experimental design. So I've got my hippity hop food and I've got my pet rabbit Lucky. All right. And Lucky, she's always just so happy. There's my pet rabbit. I'm going to use her because I don't want to pick on any of the rabbits. And since Lucky's coat is shinier and has more energy than Hippity Hop, must be the better rabbit food. So is that something I can make a claim just by using my pet rabbit Lucky? No. What's the first problem with my experiment here? Well, the fact that I don't have a control group. I need to be able to compare my food against something. So that's the first thing. We need a control group. All right, now, not all experiments need a control group as long as there's at least 2 treatments to compare. So the control group can be a nothing group with a placebo. That's perfectly fine. Or it can be the old or current item on the market. So in this particular case, feeding a bunch of rabbits nothing probably wouldn't do so well. They're probably not going to make it. So I wouldn't have a control group or a nothing group with the rabbits. Instead, I might give them the older food that was already on the market. And I'm testing my new hippity hop against it. So that's what I mean by a control group. It has to have something to be compared to. Otherwise, how do we know it's better? All right, so if you're not sure what the word placebo means, it just means a dummy treatment that has no physical effect. So things like a sugar pill, if those still exist, like here, it's nothing. You know, I just want the other group to not necessarily know, we're going to talk about it in a second, not necessarily know which one's getting the right treatment, which one's not, so I give them a dummy or something in place of the real treatment. As my students last year call it, the placebo. No, that's not it. But it's okay if you guys don't call it that. So it's okay to have fun once in a while. All right, so I know I need a control group. So let's see if this makes my experiment any better. So there's my old food. There's my hippity hop food. I'm using my pet Lucky again because he's awesome, or she's awesome. She's got a pink bow, I should say she. And now I'm going to use my friend's rabbit Flash. Lucky's going to get hippity hop, and Flash gets old rabbit food. Boom and boom. Wow, Lucky is so much bigger and shinier. Hippity hop must still be better. We're still not quite there. What do we think is still missing? Is it okay to just do like one rabbit and call it a day? No. So we need to do multiple rabbits. All right. If my food is really that good, it shouldn't matter if it's my pet or Matthew's pet or Emily's pet or anybody's pet. It should work on all of them. So I'm going to grab a bunch of rabbits randomly, and I'm just going to go ahead, and the first 5 that I catch are going to get hippity hop, and the remaining 5 are going to get the old food. So let me catch them. Throwing them in there. See, I'm even doing my physical. And the rest of them are going to go that way. Do we see a problem still? Matthew does. What do you see, Matthew? Well, what are you talking about? That's just my food doing that. That's nothing going on there. Right. So what did I not do when I selected my rabbits? Randomly. Very good. See, we're starting to learn now. So we can't just do one rabbit. We can't just do our friend's rabbit. We got to do random rabbits. So we got to go back and say, all right, Mr. G, let's do it the right way. So hippity hop rabbits are scored higher because it's better food. So it's true. No, Matthew's right. I just put all the big fat ones in mine. So we want to make sure that we find a way to randomize this. There's different ways to do it. I chose the hat method because it's easiest to illustrate. You guys could use a random number generator, whatever. But we're going to number the poor little rabbits 1 to 10. Their names are no longer important because I don't want to have any preferential treatment of these little rabbits. Put all the numbers into a hat, mix it, shake it, do a dance, whatever. And then now it's okay to pull out 5 numbers. That gets one type, and pull out 5 numbers, and that gets the other type. So number 9, you're the lucky winner. Number 7, number 5, 8, and lastly, number 3. And the rest of you is that nobody loves. Go over there in the old food. But now do we notice a little bit more variety in our selection of the rabbits? The answer is yes. So now we can sit there and say, all right, I evaluated the rabbits and found that the rabbits eating the hippity hop are better than the old food. Am I doing a little bit better at this experiment? Yes, now we're going in the right direction. Are there things that we can still do better? For sure. But this is at the base, at the very bottom of what we would need to do. Yeah, we need to randomly assign these rabbits without prejudice or without preference or whatever word you want to use in there, and be able to say that it's done in such a way that it's random. So therefore, the ones who got hippity hop did better simply because the food was better, not because the rabbit started out healthier or was a certain particular breed or anything like that. So this is the kind of things we want to talk about for the experimental process. Now, sometimes when dealing with humans, because humans are messy people, we need to do things like blinding and double blinding. So I'll write those down and I'll kind of explain what they are. All right, so with blinding, sometimes you don't want the researcher or the actual experimental units to know what their treatment is. All right, so anybody see the TV show or the movie Limitless with Bradley Cooper? He takes the pill and he's like a super focused in. All right, so a couple people. Anyways, it's a pill, and Jackson can correct me on anything I say wrong. It's basically a pill that when you take it, it opens up your brain capacity to thousands of % increase. So you never get fatigued. You're able to analyze stuff at a computer speed rate. You're physically stronger, fat, everything, it works like it's supposed to. At least that's what it claims, right? So if I don't want the person receiving the pill to know if they're receiving that treatment or not, then what I can do is something we call blinding it. So I wouldn't tell Jackson which version of the medicine he's getting. He could be getting the placebo, which does absolutely nothing, or he could be getting the super pill that's going to get him to do everything. Because if I tell Jackson up front, hey, we're going to sign you up and you're going to be a part of the super pill group, then what Jackson's going to start doing is looking for improvements in his life that may or may not be there. He's going to start psyching himself out. If you guys have ever been into a psychology class, this is where we kind of mix a little bit. Because psychology teaches that, if you convince yourself certain things are happening, then you think that's happening. Okay? The same thing it would apply here. If Jackson thinks that he's getting a super pill, he's gonna be like, man, I'm reading faster than I ever remember reading, or I'm doing math homework much faster than I ever remember doing it. And it may or may not be true. His perception of it is that way because he's telling himself that he's getting this treatment, so therefore he's getting better. So in order to avoid that kind of bias sneaking into my results, because again, as humans, we try to outthink ourselves, then I'm not going to tell him which treatment he's getting. I'm going to blind it. I'm just going to give him a pill and be like, here you go. And he's not going to know if he's getting the good one or the bad one. And then he'll come back later and report to me, yeah, I feel more focused, or no, it didn't do anything to me. And if I gave him the dummy pill, the placebo, and he's telling me all these things, I'll just know Jackson's just psyched himself out. It's a dummy pill, nothing happening. Okay. Now you can take that a step further and you can do what we call double blind, because sometimes even the researcher is adding in all of this perception. I'm all right, I'm looking around. I did everything random. But I'm adding extra results. No, I know I've seen Matthew do a little bit better with that super pill. I know that, and so I start fudging the numbers a little bit just because I can't help myself. Man, I know he's doing, I'm seeing these things, results that are not really happening. So sometimes you double blind, meaning both the person receiving the treatment and giving the treatment have no clue who's getting what and who's doing, other than you're getting bag A because that was your assignment, and you're getting bag B, and then just tell me what happens in a week. That's like a double blind. There's nobody outside of some third party observer that has a clue who's getting what. So you've already been predetermined which group you're going to be in. I, as the researcher, don't know. I'm just observing the results. Completely objective. You just say, man, whoever's getting bag A is doing really good. I don't know why, whatever, okay? So sometimes that's necessary whenever we're setting up these experiments. You might have to blind or double blind, especially with humans. Animals are a little less this way, although you can train them to be responsive too. But anyways, this little psychology mixed in with statistics here. And this is why we blind. All right, so we got our hippity hop food. Again, the claim is that it makes fur soft and shiny, increases energy for all types of rabbits. After running my simple experiment earlier where I randomly picked my 5 rabbits to go with my food and I randomly picked the 5 rabbits to go to the old food, can I now make these claims? All right, the answer again is pretty much yes. However, there's some things we still need to consider, right? There's always a well, however. So let's talk about confounding variables real quick. So the very first bullet point is your definition. This is our last definition we have to write. Hooray. So a third variable that potentially affects both the factor and the response is the confounding variable. We've talked about this before, last unit. There's lots of confounding variables. The problem with them being confounding is you don't know they exist till it's too late. So we're going to talk about how do I design an experiment to remove these confounding variables, or at the very least make them so where they're a non-factor. All right, your first bullet point underneath number 12 is the second one on the screen. It's impossible to know if the response is changing because of the factor or because of the confounding variable. This is why studies are bad. If Matthew, do you drive here or ride the bus? I'm gonna pick on you. So Matthew drives, and Matthew's typically one of my first students in class. So if I'm sitting here making a study that says those who drive get to class on time and the bus is causing everybody to be late, there's a confounding variable there. Maybe Matthew is able to leave his other class earlier. Maybe Matthew doesn't have a 5th period class because he's got privilege period in. I don't know these things. All I can see from my end of it is he's faster because he's driving. Maybe Matthew doesn't follow the speed limit. Maybe Matthew takes a different route. I don't know. There's a lot of confounding variables. So you guys see what I'm saying there? So because you don't know what the actual variable is, then you have to find ways to either distribute it equally across everything or eliminate it altogether. So this is why sometimes it takes forever to get like medicines approved for, you know, the public or whatever it may be, because if you don't answer all these questions first, then a confounding variable is in there causing havoc to your otherwise well-designed experiment. Second bullet point, similar to a lurking variable or extraneous variable. Oh, no, that's not, yeah. So basically all 3 of those names are interchangeable. Lurking, extraneous, confounding, all mean pretty much the same thing. It's something that is causing your results to be the way they are, and you did not consider it, or you don't know that. They're not fun, man. They mess up everything. Darn those real life effects. All right, a couple more things about confounding variables because they are so important. So because in studies, units can choose their treatment, there are tons of confounding variables. So if I sit on the bench again and I record that Matthew's here early because he drives, he chose to do that. I did not tell Matthew, you have to drive to the student. So there's all sorts of confounding variables now causing an issue with my study. Therefore, studies cannot be used to show causation. Because treatments are randomly assigned, potential confounding variables are either split up between treatment groups or eliminated altogether. We're going to talk about blocking. Blocking helps ensure this even more. And that way experiments can definitely tell you this causes this. So in order for me to do an experiment, if the bus or the car is faster, I would have to say they'd have to leave at the same time from the same location. And I'd have to assign, Matthew, today you're riding the bus. Lauren, today you're driving. You know, and I'd have to make sure that Lauren only goes the same speed the bus, like all that stuff, right? There's a lot of things I'd have to control, but if I did, then I could say for sure which one's faster. We can observe that the cars are faster, and I would say that's probably relatively the case, but there's so many confounding variables that it may not be just a car versus a bus thing. Other things are causing the car typically to be faster. And again, the option to obey the speed limit is probably one of the big confounding variables. All right, so to give an example of why confounding variables can be so dangerous, go back to my almost good example, but not quite, when I just assigned the first 5 rabbits I caught to hippity hop. What kind of confounding variable did I introduce into my experiment that I later got rid of by randomly assigning it? And that was typically larger rabbits are easier to catch because they slow, fat, and happy. They're probably like, oh, that guy gives me food. I'm not going to run away. Whereas the fast, skinny rabbits are probably like, bye. And so I didn't catch those. And so my hippity hop food was already starting with larger rabbits because those were the ones I could catch. So that was a confounding variable that was causing me to believe that my food was doing better when in case it may not have been. It may have been just those rabbits were already that way. All right, so that's what I'm talking about, confounding variables. So the size in this case was the confounding variable, the size of the rabbit initially. So we must connect the confounding variable to both the explanatory and the response. So they went in big, they came out big. Had nothing really to do with the food, or at least we couldn't say for certain that had anything to do with the food. So that's where we want to learn to design our experiments. And we're going to show you the three main principles here in a second. We want to design our experiments the right way so that we can say for certain that we've gotten rid of pretty much every one of these confounding variables. There's always going to be something in there we didn't think of. But if we can set it up the right way, we can make it to where we're reasonably sure something is causing something down. And that's what we want to do. All right, so before we talk about the designs, any questions so far about the terms, confounding variables? Okay. All right. Principles of experimental design. So these three things are necessary in all of your experiments. Here they are. All right, so number one, you must control the effects of extraneous variables on the response. So you can't just be all willy-nilly, we'll see what happens. It needs to be some sort of control, especially on the things that are obvious and can be controlled. Number two, and probably the most important bullet point on these three lists, is randomization. Last one that people don't often follow through with, but also very important, is replication. Can I reproduce my results with another round of experiments? If not, then maybe that first one has something in it that we didn't think about. So this kind of goes back to our simulations that we did. The very beginning of the unit, you guys set up an experiment to see how many times it's going to take, Dirk to make a free throw. I think was one of the questions on the quiz. I joked about if I run a simulation, one of them says Dak Prescott throws 6 touchdowns, but then I think like after I made that joke, the next game he like broke his ankle. So, I probably jinxed the poor guy. So what was wrong with my simulation? I just ran it once. I didn't replicate it. So over time, the more I repeat it, I would start to see a better variation of different results, and I could come up with a better average. Okay, so he's probably not going to play every game with 6 touchdowns. Wednesday. Did I forget to say that? Yes, sorry. We're going to go over that quiz on Wednesday. So I had a few people who hadn't taken them yet, so I'm letting them finish, and then I want to go through the feedback and stuff. Are you what? No, I haven't even looked at it yet. I mean, this is whatever you guys saw from Friday or Thursday, whatever you guys took it. Because I had each class I had about 3 or 4 people that were absent due to sick or field trips or whatever, I don't know, and then skipping, and haven't taken their quiz yet. So if they haven't taken it by Wednesday, then it can be a late grade, and I'm giving them an extra day. So you guys are by Wednesday. Wednesday is going to be kind of a work day review day. All right, so these 3 things, very important in your experimental design. The fact that you controlled your variables as much as possible, you randomized your selection, that's like the number one thing. If there's no randomization, don't even bother telling me the results. And then last one, can you replicate it? Is it something you can reproduce again? The results can be a little bit different, that's fine. But if you can't replicate the same thing again, then it's not an experiment. Okay. So here's the main takeaway before we talk about our different factors and things in our notes, and as far as looking at actually designing. We're going to talk about how to design one here in just a second. So the only way to actually show cause and effect is with a well-designed, well-controlled experiment. So I can play devil's advocate here with you a little bit, probably make some people angry, but that's okay. Studies show that wearing your mask prevents COVID. But they haven't randomly assigned people to wear masks and not wear masks. So there's really no way to show cause and effect when it comes to wearing a mask. It may do it, it may not. But until we do an experiment on it, it is what it is. It's just a study, right? Because you choose to wear it or don't wear it. That's not like I'm making you wear one. Yeah, the rules say to wear one, but I'm just saying. The numbers are going up or down, and they're like, well, that's because we made everybody wear a mask. Is that really what caused it? We don't know. There's other factors involved. So that's why we want to be careful with whatever information we're getting, and as far as our results and stuff. And that's not, I just picked on that because that's all in our brain. But anything that's being given to us as an observational study, was the experiment controlled? Was it randomly assigned? Was it repeatable? That kind of stuff. Okay, let's go through an example together. So what you would have to do with some of this stuff is to be able to identify from a prompt, what are our experimental units, what are our factors, what are our levels, what are our response variables, how many treatments, etc. So I'm gonna do example 1 with you, and then you guys are gonna try example 2 on your own. So I'm not talking the whole time. And then we'll see how we're doing. And then we'll talk a little bit about how to set up some experiments, and then that'll be pretty much it for today. I've got 5th period to a certain point, and I'm not gonna push you guys past that. All right, we got a farm product manufacturer that wants to determine if the yield of a crop is different when the soil is treated with 2 different types of fertilizer. Legitimate question. 16 similar plots of land are planted with the same type of seed, but are fertilized differently. At the end of the growing season, the crop yield, or the average yield, from the plots is going to be compared. So what am I doing my test on? What are my victims here? The soil. Very good, sir. Okay, so you have to ask yourself, what is receiving the treatment? In this case, the soil is. Excellent. That's your experimental units. Okay, the previous one, it was the rabbits. They were receiving the rabbit food. All right, your factors are what you're trying to test. So what are the things that we're trying to test? Somebody said it. Fertilizer, very good. So the land is receiving the fertilizer. The fertilizer is the factor that we're trying to figure out. Is A better than B, or Bob's better than Neil's, or I don't know, just making up names. Always feels like the farmer names are always like Bob's, Neil's, Jones's. All right, what are the levels? So basically, what are my different varieties of the factors here? I have how many? 2. We're gonna call them fertilizer A, fertilizer B. All right, so I got that from this part right here. 2 different types of fertilizers. So fertilizer A, fertilizer B. It didn't give us any specifics other than that, so we'll just call it A versus B. What will I measure as a response variable to know that my fertilizer did or did not do anything? The average crop yield, yes. Now, the last question is always the total number of combinations you can have. Right, or the total number of variations you can have. So how many different types of treatments are we going to have here? We're not going to do a placebo on this one. No, we're just going to do 2. Yeah, if we had a placebo, if we did a non-fertilizer, and that's not saying that's a bad thing, but if we were to do a non-fertilizer, then yes, we would have 3. But we don't need to, because we do have another comparison, right? So the manufacturer knows that you're going to use fertilizer. So instead, we're just going to see which one do we like better, A or B. That's it. But yes, very good thing. And sometimes we do need to do a non. Maybe both fertilizers don't do anything. And so we need to compare it to a nothing group. And that's fine too. Something that you guys would consider as you're doing your setup of these experiments. All right, so let me show you guys the plot of land so you know visually what I'm looking at. Everybody got these answers written down? All right, so here's our nice fancy plot of land. We broke it into 16 equal squares, 4 by 4. We got a river on the left with some trees, and then there's our plot land. So suppose the 16 plots of land are not similar. Some are obviously close to the river with trees. Others are far away from the river. Okay. If I were to be lazy and not randomly assign it, this is what I might accidentally do. What's going to be wrong with this decision? Yeah, A is close to the river, so does that mean A is necessarily the better fertilizer, or does being close to the river give it more water when it needs it? Is the soil there more fertile? Or is B get more sunlight because the trees are next to A, so B is better? I mean, I don't know, right? There's way too many questions for me to say for sure that A is better than B. So this is why the first step is very important in this, and this is randomizing. All right, so we're going to see that in just a second. So does this mean, if I set it up just like this, that fertilizer A is better if I notice that the crop yields from A come out stronger? No. We don't know if the amount of water or soil type or anything else is a confounding variable in this experiment, because I got lazy. I took fertilizer A and just went up and down the first 8 plots. Oh, that bag's empty. Took fertilizer B, went up and down, it's 8 plots. Oh, that one's done. And that's the lazy way to do the experiment. This does not answer any of your questions. It looks nice, but it doesn't do any work. So we got our first off, we're going to talk about randomizing. All right, we're going to come back to that in just a second. So just keep that in mind as we go through these examples here. So I'm going to put example 2 up on the board. And I'm going to let you guys answer the questions on what's the experimental units, factors, levels, all that kind of stuff. Okay. So again, this is not a good experiment right here because this was not randomized. All right, there's question 2. Take a couple minutes, answer those questions, and we'll see how you guys are doing. Ask away, what you got?
So like if I try to tell you if it's gonna be evenly, would my experiment going to be the case?
Yes, very good.
Okay.
Because that's what's getting the treatments, right?
Yes.
Yeah, you got it.
My levels would include the others, right?
Everything, yeah. So you're gonna have a total of 3 for the type of pan and 2 for the type of.
Okay, so do I add this?
Not add, but you did it right.
Okay.
Multiply them, and then you're all set. Yeah, pretty good.
And then, does that make sense?
Yeah, everything looks great. Now I would only just put a separation between these. So I would say like, you know, what do they call it? The pan type and oven type. Just so I mean, like you're fine that you listed them all, but I would put like a line or separation just so I would know that you understood there was 2 different things happening once. But everything looks fantastic there, like you did it exactly what I'm looking for. So no criticism whatsoever. Just as far as like a grading organization thing, like I could tell those are your first 3, and then that was your second 2. But yeah, those are perfect answers. Excellent. Right where your fingers are at is the last part. We're not going to do the matched pairs because that's confusing. So I'm going to say it once. So we're going to get up to the design part with the little box, and you guys should be able to do your first at least homework page. The notes go pretty quick once we get to this stuff here. So I think the first page you guys don't need. Yeah, the first page is just like what are the there are 4 of these type of questions. So you guys should be able to do the first page, and then the second page talks about identifying if it's a study versus a whatever, and then the third page you might have to wait on as we go through our last couple designs. But yeah, I mean, for those of you guys that like to stay caught up and be ahead, you probably do easily the first 2 pages, maybe start the third one. And then we're going to do an activity on Friday that helps illustrate all these a lot better as we're going through. Because I know some of us are like me, like I have to touch things and be hands-on sometimes to learn it because it just doesn't make sense until I've gone through it. Like you can explain it to me and it's like, that's cool. I'll figure it out when I get there. And then I have to get there. So. All right, 1 more minute. Answer these questions: experimental units, factors, levels, response variables, and number of treatments. This one's a little bit more complicated than the first one, but it's similar as far as what we're looking for. There's 2 people there. One is Danielle. That's Kate's here. Oh, somebody lost. They're gone. They can't wait no more. All right, let's do these. So number 1, what did you guys get for the experimental units? What is the victim here? What is getting the treatments? The cake batter, right? Or the cake or whatever, right? Because that's what's going to be getting treatments. It's going to get a different pan. It's going to get a different oven. So your cake batter is your victim. That makes sense? Questions? All I did, when is she still here? I didn't talk about it like all the way as far as like the steps. I just mentioned that you guys will get your groups here at the end of class. That's all for the project. Okay, what are my factors? What am I testing here? And be careful, there's 2 groups or 2 different factors. Very good, both the pan and the oven type. So you got to make sure that you know there's two different things going on at the same time, right? So you're going to fit into one of the pans and you're going to go into one of the ovens. So that means how many levels do I have? Well, for the pans, I have 3 levels, or 3 varieties. That's aluminum, glass, and plastic. And for the oven, I have 2 types. This is where you have electric and gas. Does that make sense when I say levels and factors now? I think this example is a little more clear than the first one about what I mean specifically about. So what am I going to measure for my response variable? How will I know that one is better than the other on anything that I'm selecting? Yeah, which one has a better final baking quality, or how it bakes evenly, or however you want to phrase it. Yes, exactly right. You got it right. So how evenly the cake bakes. Did one come out burnt? Is one all doughy? Like, what am I looking at? Number of treatments. Be careful on this one. So how many possible different combinations of treatment can I make from my different levels that I have? Jackson's got the right number up in his fingers. Very good. 6, right? Because I have 3 different types of pans, and each of those pans can go into each of the ovens. So I can take an electric oven and do both aluminum, glass, and plastic. I can take a gas oven, do the same thing. So whenever it comes to total final number of treatments, it's based on a multiplication thing. How many ever different varieties you have of each group, you can multiply here. Like if I have 3 pairs of shirts and 2 pairs of pants, how many outfits I got? I got 6. Although for most people that would mean you just have 2, because after 2 days you got to wash your pants and start again. But anyways, if you didn't do that, you'd have 6. We're going to talk about combinations and all that stuff our next unit. So luckily it doesn't get more complicated than this. All right, so everything here make enough sense? Any questions from me? Confusions? We okay with this? All right, so next example number 3. We change things up just a little bit to talk about some other confounding variables that we need to be worried about. And then we go ahead and actually talk about how to design your experiment here on this page, and then we're done for the day. So a farm product manufacturer, again, wants to determine if the yield of a crop is different when the soil is treated with 3 different types of fertilizers this time. So now we divided it into 15 similar plots of land planted with the same type of seed, but are fertilized differently. At the end of the growing season, the average yield from the sample plots are compared. Why would we want to use the same type of seed? Why is that important? Yeah, it's part of the control of the experiment. We don't want that extra, like, oh, the apples grew really well on fertilizer 1, but the bananas died horribly bad on fertilizer B. Okay, was that because of the seed? Is that because the fertile soil? Is that because the fertilizer was trash? Is it because it was sunnier over there? Like what? You've got all these questions now that you don't need in your experiment. So very good. Eliminate that. Everybody's getting corn. Deal with it. Or whatever crop you want. What other potential variables, extraneous, confounding, whatever, are we concerned with when it comes to this experiment? So things like the type of soil. Is it consistent throughout the plot of land, or is there like more rough clay on one side versus the other one? The amount of water all the plots are getting. Am I overwatering? Is there runoff that causes one to get flooded or not maintain enough moisture? Sunlight. Were those trees shading that one part of the land? Was the other one too much in the sun? All these things, right? And even if we can sit here and list them for hours, we're still not going to include everything. Insects, population, wind speed, right? All kinds of stuff. So we're going to try to eliminate as many as we can so that our final results are as much the response of the fertilizer only. Do we need a placebo on this one? No. And this one does not need one because we're comparing 3 different types of fertilizer. So we already plan on using a fertilizer. If the question were, does fertilizer actually enhance growth over not using it? Then yes, we would need a placebo. So look at the question carefully and decide if it's necessary. Sometimes yes, sometimes not. So like if you're trying to determine if a vaccine is actually making people more resistant to whatever, then on that one you would probably need a placebo because you're going to have people that don't take the vaccine. So does this vaccine make a difference? Not everybody necessarily getting a vaccine unless you're comparing 2 or 3 different types of vaccines against each other. Right? Different type of questions. That makes sense? So this kind of depends on what your experiment's looking for. All right. So let's talk about our different types of designs that we can do for our experiment. We're only going to talk about 2 of them today, completely randomized and randomized block. And then we'll go through an example of each, talk about the goods and the bads of each, and then we'll pause there for today and let me know if you guys have any questions. So example number 1, or the first type of experimental design, is called the completely randomized design. So this is the first set of blocks you guys see on your notes there, the blank ones. Think of this method as very similar to your simple random sample. You've got this large group of whatever, and everybody's got the same chance of getting either treatment. So the first time when I had my rabbits, I just grabbed them all up, numbered them 1 through 10, pulled their numbers out of a hat, boom. They got what they got. Everybody was just randomly assigned treatment. Nothing else specific to it. So what you're going to do when you design these experimental designs in classes, you're going to draw out a little table like you guys see in your notes here. Okay. This is what they expect on the AP exam. This is how we do this in class. This is kind of illustrates your experimental process, okay, from a left to right thing. So you start off with your first block being your experimental units, whatever it may be. So this would be your rabbits, your different plots of land, whatever. Your cake batter. Okay, so what's about to get victimized with some sort of treatment? That's what goes in the first block. And this will stay consistent every time you use this method. The only thing that will change is what goes into the blocks, but the actual format and the way it looks should be the same. All right, then you draw little arrows going through a vertical rectangle that says random assignment, which is nice because I don't have to sit there and explain my randomization process. I just have to say it's going to be randomly assigned. Yay. I don't have to write a paragraph on. I put them in the hat, 1 through 10. Randomly assigned. We got you. You're good. After they're randomly going through that assignment process, they get A or they get B, or how many ever treatments we have, C, D, E, etc. So I got my little rabbits. They got picked. Some are getting old food, some are getting hippity hop. Or I had my 2 fertilizers. So some of the soil's getting A, some of the soil's getting B. It was randomly assigned. I did not put preferential treatment to this at all. Miss Nix is really excited. She does get that with me. Okay, after you have given them the treatment, you will then measure your response. What happened from group A? What happened from group B? Bigger, smaller, more growth, less growth? Notice that I'm keeping both of these things separate. There's no crossover. There's no A gets measured by B, B gets measured by A, like it's very straight across. Keep these as independent as possible. Then at the very end, you bring everything back together and you compare your treatments. So very simple, very easy design for an experiment. Take your rabbits, throw them through a random assignment generator number, whatever thing. Divide them up by your treatments. And again, you can put on here what treatment A is. Like this is old food, hippie hop. All right. Got bigger. Didn't do anything. Or whatever. You don't have to even put the answer here. You're just going to put measure response, because you don't know what your response is going to be. So you're not going to guess ahead and say, well, I predict it's going to be that. That would be something completely different. All right. So if we look at the, go back to the farmland again with the 2 types of fertilizer, right? We got our 16 plots of 4x4 land. So instead of being lazy farmer Joe and putting all the A's on the left side and all the B's on the right side, basically all I'm going to do is randomly assign it. So I'm going to number my plot lands probably 1 through 16 or something like that. And then say, okay, plot number 1, you get A. Plot number 2, you get B, and just keep going, right? Until I've got 8 of each. So they are going to be divided equally, but not necessarily where the treatment goes. So there's my random assignment. So I decide to randomly fertilize 8 plots with A and the remaining plots with B. He gets a greater yield with fertilizer A. Does that mean that A is a better fertilizer? We can now say yes, because we randomly assigned it. We followed our randomly assigned, completely randomized design that we just went over. The effects of water and soil are more evenly spread out. So there's less confounding variables. Shouldn't say no, should say there's less. Is there a better way for me to do this though? What's a potential risk with just randomly assigning? Well, better, still not perfect. What's a potential risk here? We talked about this with sampling design too. What if I end up with 7 A's over here and 7 B's on this side? I still randomly did it, but what if that still came out to be the case? Am I still going to potentially have a problem on location? So locations really bother me as a farmer, all right? Mr. G is really concerned that the location is going to skew our results. So then if we're concerned with something like that, right, because in theory, randomly assigning doesn't guarantee that they're going to be evenly spread across the plot line. It just means I won't be picking them. If I'm concerned with something like that, then I can do what we call number 2 on our paper there, and that's using a randomized block design. It's a little more complicated, like our stratified sampling method. However, it always generates a little bit better results. Because I go ahead and I block my groups first, again, based on similar traits, and then I randomly assign the treatments. So this one's already drawn for you in your notes. We're just going to go through it. If you don't have the printed off notes, then I'll go slow enough so you can draw it. So again, you start off with what are your experimental units, rabbits, soil type, whatever. But before I start randomly assigning my plots of land to a treatment, I want to make sure that I do what we call blocking first. I want to group it. So I'm going to sort it into blocks. I'm going to sort it into block number 1 and block number 2. Now, again, what was the thing I was most concerned with on the farm example? I was most concerned about what? Location. So whatever is going to cause me the greatest concern should be what you block it by. So for the rabbits, what would be my biggest concern that might cause an issue with my results? Size. So what am I going to block them by? Size. Does that make sense? So you want to think about when I run my experiment, what could cause the biggest issue to skew my results? Let's block it by that. And then we're going to take that out of the picture. We're not going to be perfect and get everything, but we're going to get that big ugly thing out of it, whatever it is. So that's what we want to do. So I'm going to block my farmland based on location. I'll show you guys the other example in a second. Once it's been blocked, all right, plots by the river, plots away from the river. Now I can randomly assign. 4 are going to get A, 4 are going to get B. Go to this one. On the 2 farthest from the river, 4 are going to get A, 4 are going to get B. Now I'm guaranteeing that my random assignments are fairly distributed evenly, because I'm a little worried that that river is making a big difference. So I don't want all the A's or the B's to end up by the river. And then everything else from this just becomes 2 or 3 or how many blocks you have, separate experiments. Okay, so again, after you give them the treatments, you measure the responses, boom, 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 A, B, A, B. Before you compare everything, compare just for the block. So keep your results separate. You don't have to actually like do this, but just letting you guys know kind of like as you're writing your example, you would want to compare the blocks first before you compare the final results. Because this is technically a completely different experiment up here than this one is down here. And then when I'm done, I can bring everything together and say, like, okay, what do I got overall? There's my final. I noticed A was better in block 1. Oh, it was also better in block 2. A just kicking butt. Boom, that's my final answer. All right, so again, very important. Your units should be blocked on the variable that affects your response the most, the one you're most concerned about. Location, size, we'll see examples later, skill level. I'm testing a new, I don't know, basketball that's supposed to make people shoot more. If Matthew's really good at shooting free throws, I mean, I'm not, I'm just assuming. And I'm really bad at them, which is true. Then I want to make sure that he's not necessarily in the same group as me, skewing the results, if he's really good. Or if we're both really bad and somebody who's really good, them being in a, getting a, oh, wow, look how well it did to him. And those two guys did terrible. We want to block that out so we can kind of test. Okay, so whatever your biggest concern is, you can block based on that concern. It takes more time. And we're going to see this when we do our example together in class on Friday, but it's often more effective in determining actual results. So it's nice. All right, so let's go back to the farmland. What were we concerned again with is our biggest issue, location. So I blocked these two, or this plot of land into 2. Those by the river, those away from the river. Now I'm basically running 2 separate experiments. The red zone that's closest to the river is getting 4 of each. The blue zone that's furthest from the river, also getting 4 of each. Again, everything's still randomly assigned. The only thing I changed was making sure that the final results have equal numbers of it from each one. So that way, if this land over here is just notoriously going to grow corn to be 3 times bigger than anything I grow over here, well, that's okay, because A has the exact same amount on that side as it does on the other side. So we'll see what A does on either one. Does it help the bad soil as much as it helps the good soil, whatever. So this is a nice way to say that, yes, A is now the better fertilizer because we've blocked it. We've controlled the effect of that extraneous variable or confounding variable that was causing us concern. All right, so this is where I'm going to stop for today as far as the notes. Any questions for me? All right, so here's what I'm going to do. I'm finalizing your guys' group assignments. Give me like, what time is it? So I got everybody's color scheme. We got about 15 minutes, not even that much. We got like 13 minutes. Give me like 5 minutes to finish putting people into groups, and then I will show them up on the screen. And then I'll also put them in Canvas later, so you don't have to like write it down or memorize it. But start thinking about, again, for the project, which sampling design method you would prefer to do out of our 4. And then once I get your guys' group set up between now and Wednesday, just go on to Canvas. It'll be under you can message them. I'll show you guys on Wednesday if you can't find it. Say, hey, what's up? My name's Matthew. I like doing stratified if you don't mind. I'm sure everybody's gonna be okay with it. And then that's it for now. Then you go work on your independent thing and you come back and say, hey, my instructions make sense. Like Matthew looks great. Awesome. So he's actually gonna go do his sampling design from the census data. And then he's gonna write up a final report, says, hey, out of the 30 people I interviewed, he's not actually talking to them, he's just picking them off the list. It came out that the third party candidate's gonna win. And then I've had to think of a name that's not gonna anger half the class. And then whatchamacallit, he's like, this is who's gonna win the president's thing. I'm like, awesome. And then he's gonna draw a little graph that shows his results. And then you guys will talk about it in the group. So give me like 5 minutes. I gotta put everybody in the groups. I have you guys all color coordinated. I just didn't break them all off into my thing. So Zoom people, if you wanna hang in, you can. If you don't, I mean, they'll be set up without you regardless. So. All right, let me stop my recording.